So in this video lecture, we're going to cover the last section of focus 2. And this is going to be 2E and focused solely on adiabatic changes. Right? And so an adiabatic change is any change in the system that occurs where there's no transfer of heat between the system and the surroundings. And so what we're going to do is look at several different types of changes to the system. Right? And we're going to start off first by talking about what happens during temperature changes when a system expands adiabatically, right? And again, so an adiabatic system, heat is neither lost to the surroundings, nor is it either provided to the system from the surroundings. So effectively, it would be performed in an apparatus that's perfectly thermally isolated. So what we see in figure 1 is that we have some sort of initial system at T1. Work is going to be done against a movable frictionless wall as this system expands into the surroundings, right? As that work is expended, we have this new final setup of the system in which the volume is larger. And if we actually measure the temperature of the system to start with, after the work has been completed, we'll see that T2 is actually less than T1. So the temperature has fallen of the system as that system expanded adiabatically, right? So let's see if we can, so we've observed that phenomena. Let's see if we can rationalize it using some of the equations that we have and starting from the first law of thermodynamics, right? Where we know the change in internal energy is going to be equal to any heat gained or lost by the system plus any work done or done on the system. But since we're working under specifically adiabatic conditions, the change in Q has to be equal to 0. So we can rearrange that equation so that any internal energy changes must be equal to the work done that was done adiabatically, right? However, the lower internal energy, right, of this expanded system does not explain why the temperature of the gas falls directly, at least not from this equation. So we need to recall the true definition of internal energy, which is the sum of the kinetic energy and all the kinetic energy of the system plus all of the potential energy of the system, right? For when we're looking at a system that is isolated like this, there's going to be no change in potential energy of the perfect gas because there's no intermolecular forces. So we don't need to pay a price. So if there's attractive intermolecular forces, no price needs to be paid to break that potential energy. And if repulsive forces were dominant, right, there's not going to be a conversion of that potential energy into more internal energy. Right? So basically what we're left with is any change in internal energy is going to be equal to change in kinetic energy, right? And if we know based on the Maxwell-Boltzmann distribution of speeds, right, the temperature of the system is directly proportional to the kinetic energy of the molecules, right? So if work is being done by the system, right, that means the internal energy of the system is going to be negative. So if we have this decrease in internal energy and potential energy is remaining constant, then the only thing that can happen to make sure this equation is balanced is for kinetic energy of the system to decrease. So therefore, the decrease in kinetic energy is going to result in a decrease in the temperature of the system. So we know that internal energy is a state function, and this is going to help us actually calculate the changes that are going on when we went from the system at T1 under these conditions and when it expands adiabatically. Because if we look at what's happening, right, we're actually starting at an initial temperature with an initial volume, and as that volume changes to volume final, so we have this expansion, the temperature is dropping. So what we see here on this red line, this is what you observe in real life. So as they both change at the same time, which makes it difficult to calculate because we have two variables changing concurrently. But because internal energy is a state function, it's independent of path. So all we care about is the internal energy of where we started and the internal energy of when we ended, right? So what we can do is break this into two steps. Instead of following the actual path that you observe physically in real life, this red line, we can break it into two processes. One in which we have this isothermal expansion, and then what we're going to do is have an isochoric cooling, and we'll end up at the same point. And by adding these two steps together, we can actually find the internal energy change between the two states. So let's actually break that down into two steps, and we're going to follow through the calculations and see if we can calculate the change in internal energy, or derive an equation from this this process, right? So in step 1, when we're doing this isothermal expansion, so we're going from V1 to V2 without changing the temperature, right? So we've already discussed that changes in internal energy and volume are independent for a perfect gas, right? Again, that volume just increases. There's no potential energy between the molecules. All they do is just move into the new space without expending heat or expending work, right? And so in that case, the actual internal energy, if no heat and no work is actually expended, is the step 1, the internal energy is just equal to 0. And there's no change in internal energy, right? So when we look at now here at this point of this new volume at this T initial, we're going to let it cool isochorically to the final value, right? So that's our step 2. So we're looking at a change in the temperature of a system, right? So that's that decrease, so change in temperature, while volume is held constant. And we know that when we have a constant volume system, we can add, and we're dealing with heat, it should draw our attention to the heat capacity of that system. So we know the heat capacity at constant volume is going to be equal to the internal energy change with respect to the change in temperature of that system. This equation here can be rearranged, so what I can do is multiply both sides by dt. So what I do is now have du equals Cv dt, right? And so this is for an isochoric process. So we've already shown above that under adiabatic conditions, which everything is under, right? That's what we've kind of, this whole chapter, we've set the conditions that all conditions are adiabatic. We know that the change in internal energy is going to be equal to any work done on or done by the system adiabatically. So what we can do then is set these two equations equal to each other, and what we can do is derive an equation for work performed during adiabatic expansion. And that work is going to be equal to the heat capacity of that system times the change in temperature of that system. So if we integrated this would just become work adiabatic equals Cv, which we're going to make the reasonable assumption that it's constant over the temperature change, and this dt here would turn to a delta T because it would actually be a macroscopic measurable change in temperature. So what we can also do is derive an expression for the temperature change for a reversible adiabatic expansion, right? Up here, we were just looking at the temperature change of just an adiabatic expansion. So what happens when it's a reversible expansion, right? So we know reversible expansions are maximum work. They're technically, physically impossible to actually create, but it's going to be infinitely slow amounts of expenditure of work. So you physically can't do that because it would take infinite amounts of time. But the consequence of that is as that work and as that volume expands, right, or as that temperature changes in this case here, right, it's going to be happening at equilibrium. And so if it's a reversible process, that means the pressure is going to be equal to the external pressure and whatever the pressure is of the system. They should always be in mechanical equilibrium. So if we start with this equation we derived above, where we have the adiabatic work is equal to the heat capacity times the change in temperature of the system, right? We've also figured this out in focus 1, where we know reversible work is equal to minus PdV, right? And that P can either be the pressure of the system or the surroundings, because theoretically they should be equal because they're at equilibrium. So what we can do now is if we're under the conditions of a reversible adiabatic expansion, I can substitute the work of a reversible process for the work of the adiabatic process in this calculation, and we end up with this new expression that Cv dt equals negative PdV. Right, so we have two infinitesimals in there. So let's see what we can pull out of this information. So if we assume the gas behaves perfectly, what we can do then is here we have the P, we can substitute in the ideal gas law here, right? The substitution results in, so nothing happens to the left-hand side of the equation, but now our P is equal to nRT over V. And what we were trying to do, the reason why we want to do that is because we have this infinitesimal dV here. Well, we need to have volume here to actually calculate the integral. So now we have an equation on the right-hand side that has the infinitesimal as well as the volume, well as the variable of that infinitesimal, which is volume, right? So what we can do here is also divide both sides by t, because if we look at the left-hand side of the equation, so we've taken care of this infinitesimal with this variable. We have another infinitesimal for t, but I don't have t on the left-hand side of the equation. So what I can do is take the t that's over here, bring it over here, and that's what we see here. It's effectively dividing both sides by t. So CV over T dt equals negative NRV dV. So now we can integrate both sides, the left-hand side as the temperature goes from T initial to T final, and the right-hand side from V initial to V final. So we already made the reasonable assumption that the heat capacity at constant volume is going to be constant over the temperature range. Obviously, it was an enormous temperature range. We know that CV does change, but we're going to make the reasonable assumption that we're looking at a small enough temperature change that CV is constant, so we can take it outside the integrand. And the same thing as everything in this beginning chapters, we're taking that then the moles of the system are going to remain unchanged. We're not adding moles, we're not taking away moles, and there's no chemical reactions. And then R is obviously constant, so those can be taken outside the integrand here. When you take the integral of 1 over t, you're going to get, it's going to be the natural log of that variable. So when we do it for this definite integral, it's the natural log of t final minus the natural log of t initial. And over here we have the same effect going on with the volume. There's the natural log of v final minus the natural log of v initial, with all the constants taken outside. We can apply log rules, so when you subtract two natural logs, that's the same thing as dividing whatever was inside the parentheses. So there's our CV ln, the ratio TF over TI, equals negative NR ln, and the ratio v final over v initial. To get rid of this negative sign here, we can apply additional log rules, where now VI over VF is our ratio. That changes the sign on the outside to a positive, so now we have this equation. If I divide both sides by NR, I bring them over to the left-hand side, I have this equation. And to make our lives a little bit easier, at least the math, what we're going to do is we're going to take this variable here, CV over NR, right? It's basically lumping all the constants together, and so we'll call it a new constant, little c. So we have our lowercase c. It's basically, here we can see CV over N has just been converted to the molar heat capacity at constant volume. So now we have C times the natural log of the ratio of the temperatures equals the natural log of the ratio of the volumes. So this one, we need to reach more log rules. So if we have some number a on the outside of the ln of some variable x, it's going to be equal to if we took the natural log of a to the x, x to the a. So in that case, applying this mathematical rule, we can take c, which is on the outside of this natural log, and bring it onto the inside. So now we have the natural log of the ratio of the temperatures raised to the cth power equals the natural log of the ratio of the volumes. So if we exponentiate both sides, so we're basically raising both sides, so it's e raised to the power of these variables, and e raised to all of this. So effectively it cancels out the ln's, and we're left with this equation. If I take the cth root, so it's like taking the square root, but instead of taking the square, it's being base 2, the radical is going to be based on the cth root. So that cancels the c's there and leaves us with 1 over c on the other side. Right, we can rearrange this equation, so we're solving for TF. And then if we then raise both sides to the cth power to undo this cth root here, we'll end up with this equation here. And one last rearrangement, we can come up with this equation here, right, where the temperature change for a reversible adiabatic expansion of a perfect gas. So we're under two conditions which actually you can only approximate in real life. We know reversible processes are not a real thing. We can approximate it pretty well, but reversible processes inherently take infinitely long times to complete, so they're technically impossible. And the same idea with a perfect gas. No, there's no such thing as a perfect gas. But this does give us, as long as we're under the conditions where we can make reasonable assumptions that it's quasi-reversible or semi-reversible, basically we can approximate reversibility, approximate a perfect gas. This equation will hold. Right. So what we've done here is observe changes in temperature, and we ended up with two equations. So for you guys, what I want you to take home from this is have our equation here for the adiabatic, the work done for an adiabatic expansion, as well as this temperature change for a reversible adiabatic expansion. So they're technically under two different conditions, solving for different things, but being able to know where those equations came from as well as being able to use them is going to be critical aspect of this chapter, right? Like I said, a lot of this particular chapter is deriving new equations, being familiar on how to use them, because what we're going to use these equations in further chapters. So basically this section is just, let's get a bunch of equations and see if we can basically add it to our repertoire. So what I'm going to do is I'm going to break up this video into a couple of sections. So this is just going to be dealing with the first section of topic 2E, which we were dealing with temperature changes. And the next section, what we're going to do is deal with changes in pressure.